In this video, I will explain that how I have developed the machine state model in AnyLogic software. I have developed two separate programs, one for the always on policy and the other for the RL policy. In this video, I will explain the working of always on policy. The machine, the basic layout for both the programs is same. It consists of 4 stages, with the machine block 1 representing the first stage, then machine block 2 representing the second stage. Similarly for the machine block 3 and machine block 4. Machine block 1 consists of 3 machines in parallel. This is the logic for a single machine, then machine 2, and then machine 3. And the machine block 2, there are 6 machines in parallel. Machine block 3, there are single machine. Machine block 4, there are 2 machines in parallel. The process flow starts from the source block. The purpose of the source block is to generate parts, and its arrival is based on an exponential value which is derived from the literature. And it will create agents known as parts. The source will generate parts exponentially. Then comes the buffer, then machine block 1, machine buffer 2, in the similar way it goes on. Here you can see some icons. The purpose of these icons is to represent the current state of the machine, and whatever will be the state it will turn into, the icon will glow up. Here you can see some blocks, machine 1, machine 2, machine 3. These are resource pool blocks. The purpose of the resource pool block is to model the resource, and it works in a way like you can see here. Once the part comes in, the seize block here will seize the resource, which will be defined in the seize block. In the seize block, I've defined resource pool block. I have defined resource pool block as a machine, which I will show you in this video. I've just selected machine block 1. And in the machine block 1, I have just selected these resources, machine 1, machine 2, machine 3. So this seize block will seize the resource as machine resource. The machine resource will process the part. The part will go through startup and processing, and when it's done, the resource will be released. In this case, machine 1 will be released. This is downtime block. It is used to model the fate state. I have defined this downtime block in machine 1. Whenever I have to called for a downtime, which will be based on a stochastic value called TBF, total time between failure. This downtime block will be called on in the machine 1 block, in the resource pool block, which is called here machine 1, and it will model the downtime. And once the downtime occurs, I have used another resource pool block known as repair personnel. The repair personnel will go and troubleshoot the machine. Here you can see that once a downtime occurs, a repair personnel will come in and he will troubleshoot the machine, and that troubleshooting time will be based on TTR, total time to repair. And once it is repaired, the resource pool of repair personnel will be released, and in this way machine will again go back into its working state. These all blocks work with some logic, and the logic is defined using coding in Java. I have coded it in Java, as you can see the whole of it. This is for machine block 1. In the similar way, I have defined logic for machine block 2, machine block 3, and machine block 4, and defined individual uh, blocks as well. Like in the case of source, I've defined exponential value. I've selected the agent. Now, to in order to work, let the log simulation work as as per my as per my assumptions that I've made. I have to model it in a way which so that it could work according to the assumptions made in the methodology section. So here you can see I've defined different parameters and variables and functions to make the simulation run. Like I've defined selector variables, for selector function, I've defined different logic here. So in this way, this whole program works. Now I will just run the simulation. Here you can see that in the start, all the machines are in idle state. And once the part will come in, it will go through the startup phase just for the first start. After that, it will not go through a startup phase because in the on always on policy, basically it works in the four states. It's either idle, busy, and failed state. And if the machine goes through failure, it can only go back to the start working phase after passing through the startup phase. In this always on policy, no standby state is used. So in this way, this graph shows the current energy status and it shows how many parts are produced and the current throughput.